My name is Brendan Banfield, and my project for ECTE451 is the technical and economic benefits of utility-sponsored renewable energy integration. In recent years, the level of distributed generation, particularly solar photovoltaic generation, has been increasing rapidly throughout Australia. This rapid increase in DG has led to voltage regulation issues throughout LV networks. Currently in Australia, distribution network service providers, or DNSPs, have had very little involvement in residential solar PV beyond connecting the system to the LV network and providing a feed-in tariff for any excess energy that's exported back to the grid. If DNSPs were able to provide services related to solar PV that guarantee customer income, minimise customer disconnects, and provide energy storage as well as voltage control capabilities, there could be potential benefits for not only the DNSP but the customers as well. It can have several adverse effects on distribution networks. This can include an increase in harmonics caused by the high-frequency switching of the power electronics in the solar inverter. Islanding can occur when a distributed generator supplies power to a part of a distribution network that should be de-energized. Voltage fluctuations can occur when cloud cover blocks out the sun. This causes solar PV power output to drop, which in turn causes voltage fluctuations throughout the network. Voltage unbalance can occur when a large amount of solar is connected to one phase. Finally, voltage rise can occur when the power from a distributed generator begins to flow back up the network towards the distribution transformer. The following circuit is a simplified distribution network. V-grid is the voltage at the MV-LV transformer. The DG can be treated as a current source with its voltage defined as VDG, and the line impedance and line current are defined as Z and I respectively. When the DG is exporting no power back to the grid, the voltage at the distribution substation will be higher than that at the customer's premise. For this reason, DNSPs often have the voltage at the distribution substation set higher than nominal to account for the voltage drop along the feeder. The phasor diagram for this scenario can be seen on the slide. As you can see, V-grid has a larger magnitude than VDG. During periods of light feeder loading, which can occur during the middle of the day in residential areas, the amount of power generated from solar PV can be greater than the local load demand. The power that is not being utilised by the local load is then supplied back to the grid. This subsequently causes the flow of active current to reverse along the feeder, and in turn can lead to a voltage rise along the feeder. Again, this is illustrated by a phasor diagram. Here VDG, the voltage at the customer's point of connection, is greater than that at the distribution substation. For this reason, several electrical utilities in Australia have limited the installed capacity of solar PV on the distribution feeder to be around 30% of the peak power demand on that feeder. By incorporating energy storage with solar PV, the excess power that would usually be supplied back to the grid during periods of light feeder loading can be used to charge the energy storage units. This can assist in reducing the reverse power flow in a network and thus can aid in reducing the occurrence of overvoltages. A potential short-term solution to mitigate overvoltage in a distribution network is to tap down the distribution transformer. By selecting a lower tap setting at the distribution substation, it is less likely that the reverse power flow from DG will cause the voltage to increase above the limits set by the regulator. Finally, voltage rise can be reduced by having the solar inverter shift its power factor to begin absorbing reactive power. This can either be achieved using a decentralized control scheme whereby the inverter adjusts its power factor based on the voltage at its point of connection, or by a more centralized approach, where the DNSP would send all inverters a command to adjust their VAR output according to an overarching control scheme. Many utilities around the world are beginning to implement centralized control of their inverters. The Hawaiian electrical company, HECO, was able to reprogram 800,000 microinverters in their network in one day. The purpose of this reprogramming was to have the microinverters ride through irregularities such as substandard AC voltages and frequencies, as opposed to simply disconnecting. HECO planned on reprogramming the microinverters to begin absorbing reactive power to assist in reducing overvoltages in the future. Southern California Edison, a utility in the United States, is currently in the process of upgrading their current standards to allow for smart inverters to participate in voltage regulation. The decision to allow smart inverters in the SCE network to participate in voltage regulation follows the success of utilities in Germany, who implemented similar standards whereby smart inverters begin absorbing reactive power when the output from the solar PV exceeds 50% of its rated capacity. German utilities are able to install 40% more PV capacity on the same line with this functionality. The following section explores both a centralized and decentralized control scheme that could be used to reduce voltage rise caused by solar PV in a distribution network. The simulations were performed using 3 pieces of software. Dixelant Power Factory was used as the load flow engine, MATLAB was used to implement the reactive power droop control for each inverter, and finally, Excel was used to handle the large amount of load flow data that had to be interfaced between Power Factory and MATLAB. The network model in Power Factory consists of one distribution substation with a 400 kVA transformer. The substation has 2 LV feeders and supplies 88 customers, 27 of whom have solar installed at their house. The combined rated capacity of installed solar is 86.8 kilowatts, which gives a total DG penetration of 21.7%. The Droop characteristic developed for determining the required reactive power consumption of each inverter was based on an inverse sigmoid function. The y-axis corresponds with the per unit reactive power, while the x-axis corresponds with the per unit voltage. Q varies between 0.436 per unit and negative 0.436 per unit, which corresponds with a power factor of 0.9 leading or lagging, respectively. The voltage varies between 0.95 and 1.05 per unit. If the bus voltage in an inverter is higher or lower than either of these set points, the inverter will automatically drop its power factor to 0.9. The distribution network in Power Factory before the droop control was applied is shown here. The orange nodes represent voltages that are above 1.06 per unit. Phase C, which has the highest average voltage before the droop control was applied, at 1.065 per unit. This is the network after the decentralized control was applied. As you can see, there are no longer any orange nodes indicating voltages above 1.06 per unit. For the decentralized control, the voltage at each inverter's point of connection was applied to the droop characteristic. From the droop characteristic, each inverter was assigned a new operating power factor. The per unit bus voltage along phase C as a function of the distance from the feeder head can be seen here. From the graph, it is evident the average voltage on phase C was reduced significantly after the droop control was applied. The network after the centralized control was applied can be seen here. Unlike the decentralized control scheme, each inverter is assigned the same power factor, based on the average voltage across the entire feeder. This ensures fairness among customers, as no one is absorbing a higher percentage of reactive power compared to anyone else. The per unit bus voltage along phase C as a function of the distance from the feeder head for centralized control can be seen here. From the graph, it is again evident that the average voltage on phase C was reduced significantly after the droop control was applied. The following proposes a potential business model relating to how a utility could implement residential solar PV management systems throughout their network. Each residential system will consist of solar PV, a smart inverter that will be owned and controlled by the utility, as well as some form of energy storage. The model is split up into 3 stages. The first stage involves the utility approaching the customer offering to make a quote on an energy management system. If the customer is interested, the utility will undertake an analysis to determine the optimal size of the solar PV and energy storage, as well as the predicted payback period and value of the investment over 15 years. Stage 2 involves the utility sending a technician to install the system and establish communication between the smart inverter and the utility's supervisory control and data acquisition, or SCADA system. Finally, stage 3, system operation, involves the utility using the smart inverters that have been installed as a part of the utility-sponsored scheme to regulate voltage throughout the LV network. The utility will also have the potential to discharge the energy storage unit to either supply customer loads or be exported back into the network to perform peak shaving during peak load periods. The potential costs and benefits for utility-sponsored solar PV present several challenges. To gain an in-depth understanding on these costs and benefits, the utility would require extensive research followed by benchmarking trials to establish whether or not the system is truly feasible. For this reason, the costs and benefits for utility-sponsored PV were not quantified. The main costs a utility would have to consider, however, when investing in residential solar PV include the cost of each smart inverter, sizing each energy management system on a customer-by-customer basis, system maintenance and operation, and finally, the communications infrastructure. If this communications infrastructure is leveraged from current protocols the utility uses, such as the Distribution Network Protocol, IEC 61850, or the Advanced Metering Infrastructure, the cost could potentially be decreased. However, communications is an area that would lead to significant CapEx investments for the utility. For utilities investing in residential energy management systems include the deferral of CapEx investments through increasing asset life and deferring the need for network augmentation, reduction in the utility's annual systems average interruption duration index, as well as their systems average interruption frequency index. This could be potentially achieved by dispatching a number of generators during an outage to operate as an islanded microgrid, or by simply supplying loads via energy storage units during outages. Other benefits include the ability to overcome revenue erosion by feeding electricity back into the grid at a higher price than wholesale. And finally, the utility would be opening up an entirely new revenue stream in the emerging DG products and services market that wasn't previously available to them. To determine the costs and benefits from the standpoint of a customer, 3 scenarios were considered. The first scenario being a customer who has no solar PV. The second scenario is a customer who has privately owned solar PV. And the third scenario is a customer who invests in utility-sponsored energy management system. For all of the scenarios previously mentioned, a customer load profile is required to determine the average amount of energy the customer uses annually. A per unit load profile for residential customers was obtained from the DNSP in Canberra ActuAGL. This per unit load profile can simply be multiplied by the customer's average daily power consumption to determine an average daily load profile for that customer. 3 scenarios will consider the customer's average daily power consumption is 1 kilowatt. This analysis will also use ACT residential electricity prices, which can be seen here. By integrating under the load profile curve, the average energy used by the customer per day can be calculated. From that daily energy usage, it was calculated that the customer would spend $1,790 annually on electricity. This figure shows the customer load profile in blue, along with the average daily output of a 3 kilowatt PV system in red. Both these curves were used to calculate the associated costs with scenario 2 and 3. For scenario 2, the customer with privately owned solar PV, it was calculated they would spend $1,177 annually on electricity. That is $612 less than the customer who had no solar. Considering the average price for a 3 kilowatt system in Australia is $5,288, this gives a payback period of 8.64 years. To verify the investment is worthwhile, the net present value is calculated. Net present value analysis reduces all costs and incomes to a value in the present. If the net present value is positive, the investment is worthwhile. The net present value was calculated considering an interest rate of 6% over a 15-year period. The net present value was shown to be $655, therefore the investment is worthwhile. To calculate the initial cost of the energy management system for a customer, the price of the smart inverter will be subtracted, as it will be purchased by the utility. However, the cost of the energy storage unit will need to be added. Lithium-ion battery technology will be considered for the energy storage unit due to its high charging density, low self-discharge, high charging efficiency, and its life expectancy of 15 years. Prices for lithium-ion batteries have been decreasing rapidly in the last few years, and currently cost around 0.5 of an Australian dollar per watt hour. Considering a 6 kilowatt hour battery, the cost of an energy management system for this particular customer would be $6,966. It was then calculated the customer would spend $1,052 annually on electricity, saving $736 compared to scenario 1. The payback period was 9.49 years, with a net present value of $186.41. Although this net present value is lower than the privately owned scenario, it does not take into account the discounted price a utility would be able to sell a solar PV system to their customers. If the utility were able to sell the system at 85% the cost of retail, the payback period for the energy management system goes down to 8.65 years with a net present value of $755. Future work for this project includes developing a more sophisticated centralized control scheme that implements 4-quadrant control with the supply of active and reactive power from the inverter, as well as the charging and the discharging of the energy storage unit. This control scheme will then be simulated over an entire zone substation, as opposed to one distribution substation. This will give an insight to the effect coordinated control of solar PV has on a larger portion of a distribution network. Further investigation into quantifying the potential economic benefits of utility-sponsored PV will also need to be explored to determine whether or not such an investment is truly feasible for a utility. Thank you.